So the first thing that should come to your mind when we talk about pulley is this diagram. So I have a very simple problem here. You can clearly see there is a 2 kg block, there is a 5 kg block, and we have to find the acceleration. We have another situation. You can clearly see there are multiple pulleys, 1 pulley, 2 pulley, and this pulley is fixed, while this, what is acting downward is 3G, what is acting upward is 2T, what is acting upward is 2T, but what is acting upward is T. Be very careful. So what is this wedge constraint thing? So you understand string constraint means.
Hello students, welcome in today's class. In today's class, we will talk about majorly two different concepts. One is related with pulley, specifically multiple pulley problems, and second is related with constraint relationships. That is further divided in two parts, string constraint and wedge constraint. This class is going to be very exciting as many questions are directly asked based on these concepts. So I hope you will be able to learn with us and at the same time enjoy learning with us. Alright, so I think we shall start. So the first thing that should come to your mind when we talk about pulley is this diagram, and very quickly let's again revise that for now we will consider the pulley to be ideal. So this is an ideal pulley, and by ideal pulley we mean that it is frictionless. So the tension on the two sides of the pulley is the same. Secondly, we consider the string to be ideal as well, which means that it is inextensible. The string is inextensible. Its length cannot be changed. Alright. So when this diagram comes to your mind, you will quickly draw the free body diagram, and that is going to be mg downwards for m1 and tension upwards. Similarly, tension upwards and m2g downwards. So this is the basic pulley problem that I am discussing for reference for further problems. Alright. So now you will say, let's say m2 is greater than m1, then it should fall while m1 should rise. Now if you see, I have written accelerations a1 and a2, but you can clearly imagine that these two need to be equal. Now why do you say so? That is because you would say that length of the string cannot change. So if this side, let's say, descends by a distance x, so the length of the string increases by x. But since the total length cannot change, this side has to move up by the same distance. So whatever is the gain in length on the right side has to be compensated by a loss in length on the left side. That is why, since these two displacements are same, that clearly would mean that a1 is equals to a2. In a way, you have used the string constraint relationship because you are using the fact that length of the string cannot be changed, and there is a constraint that if this side is increasing by some distance, then this side has to decrease by the same distance. So now in a way you know what exactly string constraint would mean. You can draw this diagram, you can have a go at this. So you at the same time you can now write that, let's say if a1 is equals to a, then a2 is also equal to a. So both the accelerations are equal and opposite, equal in magnitude and opposite in direction. How do we use this in the further problems? We'll quickly discuss that, but I'll give you time to copy this down. Now very quickly, the next thing. So I have a very simple problem here. You can clearly see there is a 2 kg block, there is a 5 kg block, and we have to find the acceleration of the two blocks. Now very quickly, one by one we will draw the free body diagram. So alright, so let's first draw the free body diagram of 2 kilogram, let's say. Okay. So the first thing that you will apply is mg downward direction. Okay. And let's say there is a tension, that is the pulling force, as you know, in the upward direction. So this string is going to pull, and I can you can clearly relate that it is one string only. So this is entirely one string. So let's assume that the tension in the rope is T. So it will be uniform, it will be same throughout, it won't change. Why? Why do I say so? Because we always assume string to be massless. Okay. So you would say, fine, this is the force, this is the force. Is there any other force? So for that you need to understand how this system is moving. So because of gravity, this 2 kilogram will start descending. Because of gravity, of course, you can imagine this 2 kilogram block will start descending. So when it will start descending, the length of the string will start increasing here. It will start increasing here. Okay. And if it has to increase, the length has to decrease somewhere else. So where is it decreasing now? Think about it. Can this length ever change? No, this length is constant. This length can never change. These two pulleys are fixed. So what happens then? Whatever is the gain in length here has to be compensated by the loss in length here. So let's imagine that this block moves by a distance x dash forward. This block moves by a distance x dash forward. So this x dash will cause a loss in length of the string by x dash here as well as here. So can we say that the gain is equal to the loss? Yes, of course. So can we write that x is equals to x dash plus x dash? That is, x is equals to 2x dash. One more time. This is how you're using string constraint. There is an increase in length here and there is a decrease in length here also and here also. So these two decrease combined should be equal to this increase. So let's say the block 5 kg block displaces by x dash to the right, then the 2 kg block should descend by x, then x is equals to x dash plus x dash. Now this is proportional. So this displacement is proportional to the acceleration of 2 kg downward and this is proportional to the acceleration of 5 kg forward. So if I differentiate this once with respect to time, you all should understand, then v is equals to 2v dash. Similarly, if I again differentiate, then it is a is equals to 2a dash. This is how you are using string constraint. Alright. So can we say that the acceleration of this is a downwards? But there is a catch. Do you think that 2 kg is only moving downwards? Or does it also move forward with 5 kg? Of course it will, because we are studying rigid body dynamics. What are we studying? Rigid body dynamics. So if 5 kg is moving forward, 2 kg will move forward with it as well. So in the acceleration diagram in the first place, 2 kg will not have only an acceleration downwards, but it will also have an acceleration forward. And therefore, there will also be a normal contact force. Basically, who's pushing the 2 kg block? It is the normal contact force of the 5 kg block. So this class is only for those people who know the basics of laws of motion, how normal contact behaves, how tension behaves. So if you don't know that, then you'll need to go back to the videos and see those things first. Alright, so this is the free body diagram. Now can we write the equation in x and y? So what would we write? 2g minus t equals to 2a. Why? Because it is ascending, it is descending downwards. Now for this is for y direction. What about for x direction? You would write n is equals to 2a. Okay, so this is first equation, 2a dash, and this is the second equation, a dash, because a dash is the acceleration in the x direction. So clearly you have framed two equations here, and the number of variables are 4 in fact, n, t, a and a dash. So you need two more equations. Alright, so for that what we need to do is, okay, so in fact there is one more equation already, that a is equals to 2a dash. So there are three equations. We need one more equation to solve this problem entirely. Who will give us that equation? Obviously 5 kilogram block. So if we talk about 5 kilogram block, I am drawing the free body diagram in this itself. Okay, and let's show the forces that are acting on the 5 kilogram block. But before that, keep that in mind, whatever forces are acting on this pulley will be treated as part of 5 kilogram only, because 5 kilogram and this pulley are attached with each other. So whatever forces you're showing on the pulley should also be shown on the 5 kilogram block. Alright, I think we can start. So this is the first tension in the rightward direction. I think I should use a different color here. Let's say, all right, I will use green color only. So this is, let's say, T, okay, and this is another T, okay, this T and this T. Both the tensions are same because it is an ideal string. Then obviously 5G acting in the downward direction. Then there is a normal contact, let's say N dash, that is because of the ground on the 5 kilogram. Next is the same N as 2 kg is experiencing to the right, it will give the same reaction to the 5 kg in the left direction. So one last force is left now, that is the tension again because of this string. So are we ready now? Have we drawn all the forces on 5 kilogram? There is mg, there is n dash, there is n, and there is tension, there is one more tension, and then there is a tension vertically downwards. But we are only interested in writing the equation of 5 kilogram block in the x direction. Why? Because if we draw the acceleration diagram here, it is clearly, first of all, a dash in the rightward direction and no acceleration in the vertical direction. So 5 kg is not moving up and down, it is only moving to the right. So what will we write? The net force to the right is T plus T minus N. Look at it again. T is rightward, T is rightward, while N is leftward. So we are writing in x direction for the 5 kilogram block. Should we be writing 2T minus N is equals to 5A dash? 2T minus N is equals to 5A dash. This will act as our fourth equation. So there are 1, 2, 3 and 4. So 1, 2 and 4 are something that you must be writing so far. This is something new. This is called the string constraint. Let's revise this equation again. How did we get this equation? By a simple logic that a gain in length somewhere has to be compensated by a loss in length somewhere. So where is the increasing length here? It's only this part of the string. So when this part increases in length, these two parts need to decrease in length. And that is why we said that, let's say this moves x downwards, then because 5 kg moves x dash forward, so x is equals to x dash plus x dash. Is that fine? Think about it. And once we have the relation in displacement, we can clearly relate the acceleration by differentiating it twice. All this is being done assuming there is no friction. So obviously we are not involving friction today, and we are doing just, focusing on the constraint part and the multiple pulley part. So this can also be treated as multiple pulley in a way, because you see there are 3 pulleys here, and this pulley is very special because it is a movable pulley. These 2 pulleys are fixed pulleys. So I'm not solving this, so you can solve it yourself to get the value of all the 4 variables, which are N, T, A and A dash. This is just to give you the concept that how all these forces operate and how do we use constraint. So far you were always assuming that if someone is falling with A, the other thing will rise with A. That is not true here. If this is falling with A and this is moving forward with A dash, then A and A dash are not equal. Keep that in mind. I will wait, you can copy this down and then we will move forward. So when I say I will wait, you have to pause the video and copy the solution. And don't take it as a solution, like it is something I wish to teach the concept through the questions. That is the idea. Alright. Now, we have another situation. You can clearly see there are multiple pulleys. 1 pulley, 2 pulley, and this pulley is fixed while this pulley is movable. How can you realize that it is movable? It is fixed with the 3 kilogram block. And since the block will move, this pulley will also move. Now again, you would want to believe that the acceleration of 2 kilogram upward should be equal to the acceleration of 3 kilogram downward. But that is not true. That is only true if one string is connecting these 2 blocks. Here you can see there is another string here. Okay. So let's take things one by one. One thing, but you have to assume the accelerations now. And some of you might be wondering that, as always, 2 kilogram being lighter should rise and 3 kilogram being heavier should fall. Even if we believe in that, I will ultimately prove that it is wrong, and in fact 3 kilogram will be rising and 2 kilogram will be falling. So which is like, very contradictory to what we were doing so far. Lighter things always rise and heavier things always fall, but here the heavier one will rise and we will find out why. But for now, purposely, let's do one thing. We can also assume the accelerations in one direction, all accelerations downward or all accelerations upwards, and automatically we will understand how things are changing. So let's start. So the first thing that you should do is draw the free body diagram. So 2g is acting downwards. This is, let's say, t. For 3 kilogram, 3g is acting downwards, and this is, let's say, t dash. So we would refrain from calling it t, because this tension is the tension in this rope, but this is another rope or linking thing that can have a different tension. So for that relation between t and t dash, I am drawing the FBD, or the free body diagram of the movable pulley. What am I doing? I am drawing the free body diagram of the movable pulley. All right. So this is the movable pulley. I will show the tensions very quickly here. So this is T, this is also T, while this is T dash. Okay. So when I'm drawing the free body diagram of this pulley, of course, rope can only apply a pulling force. So this rope is pulling upwards, this rope is pulling upwards, while this rope is pulling it downwards. It's not the free body diagram of 3 kilogram, it's the free body diagram of the pulley. So what can you see here very quickly? That since mass of the pulley is always taken as 0, so what can we say? T dash minus 2t equals to ma, but m is 0. We assume the pulley to be massless. So that means T dash is equals to 2t. So this is one relation between the tensions first, that if the tension in this rope is T, then the tension in this rope that is attached with the pulley is always twice of that. So the tension in the rope which is passing over the pulley and the tension in the rope which is attached with the pulley, this tension is always twice of the rope passing over the pulley. Keep that in mind. Okay, so what are we doing here? How are we starting? Let's assume the conventional thing. Let's assume that this is rising up with A and this is falling down with A dash. Ultimately, if we will solve it, we might get an abrupt result and we might get negative accelerations, which would clearly mean that the assumed direction is incorrect and the system is accelerating in the opposite direction. Okay, let's do it very quickly. For 2 kilogram, you will write the force equation. So it should be T minus 2g equals to 2a. There is no doubt about it. T is upward, 2g is downward. T minus 2g is equals to 2a. Now for 3 kilogram, okay, what is acting downwards? 3g. What is acting upwards? Can I straight away write 2t now? Because T dash is 2t. So I'm straight away writing 2t is equals to 3 into a dash. Now effectively we have two equations, but there are three variables, T, A and A dash. So again we need one more equation, and who's going to rescue us? So the answer is constraint relationship. What is it? Constraint relationship. Imagine that this falls by x dash. This falls by x dash. How much rope is elongated here? You would say x dash. How much rope is elongated here? Again x dash. So x dash and x dash. So on this side there is a gain of 2x dash. So it has to be balanced by this loss. So can we say if this rises by x, then x is equals to 2x dash. Let's do it again. It falls by x dash. That means the length of the rope increases by x dash here also and here also. So it's a total gain of 2x dash. That has to be balanced by this. So the loss is, let's say, x. So this loss is equal to this total gain. So x is equals to, should I be writing it like this? Let's say first x is equals to x dash plus x dash, which means x is equals to 2x dash. And since we have related the displacement, what we can do is we can differentiate it twice. So this will become a is equals to 2a dash. I have differentiate twice. And what does that give me? A is equals to 2a dash. Now I have the equation. What do I need to do to solve this? I need to put the values. Let's do it. Let's in fact solve this. So for that, what I am going to do is I'm going to put the value of a first. It's going to be t minus 2g over 2. So I'm using the first equation to put the value of a. Let's call it the first equation. Let's call this as the second equation. Is equals to twice of a dash. So what is a dash now? 3g minus 2t over 3. So now I have an equation which is purely in terms of t. So what can I do here? What can I do? So let's say 3t minus 6g is equals to 12g minus 8t. So this gives me 11t is equals to 18g, or this gives me t is equals to 18g over 11. This gives me t is equals to 18g over 11. Once I have the value of t, I can put it in first equation and get the value of a. So when I do that, 18g over 11 minus 2g equals to 2a. So what are we getting? 18 minus 22 minus 4g by 11, and if we divide, so we get a as minus 2g by 11, and therefore a dash, which is half of a, is going to be minus g by 11. So what are these minus signs telling you? So these minus signs are telling you that whatever we have assumed as the direction of acceleration is incorrect, and in fact 2 kilogram is not rising but it is falling, and 3 kilogram is rising instead of falling. How does that happen? How can a heavier thing fall and a lighter thing, how can a heavier thing rise and lighter thing fall? How can 2 kilogram fall and 3 kilogram rise? So it kind of feels as if the energy is being created. So this is the concept of perpetual pulleys or power generating pulleys, which is only an illusion. There is no power created. There is no motor here. What happens is that if you look at it closely, gravity is 2g on this and 3g on this. So the gravity acting on 3 kilogram is 1.5 times. But the upward force becomes twice. So that dominates. And this starts rising. Imagine, for example, if this would have been 4 kilogram, you know what? The system would have been in equilibrium. Why? If it is 2 kilogram, if it is 4 kilogram, the gravity force becomes twice, and so is the tension. So in a way, T and 2G and 2T and 4G, it's like equivalent, and there won't be any acceleration. So this is how, apart from hydraulics, we can think of lifting up heavier things by, connecting them with multiple pulley arrangement. They can amplify the effect of force. That is how it works. So let's look at it one more time very quickly. We assume that this is rising and this is falling. There's no problem if we assume it incorrectly, because ultimately the answer is correct and the sign is negative. That means the direction is opposite. So there's no problem even if we have imagined that, this is going up with a and this is falling down with a dash. So how did we solve this equation? This thing you can keep in your head all the time now, that whenever there is a arrangement like this, for example, even for this one, if the tension here is T and here is T, then the tension here is going to be T dash, that is going to be twice of T. So we will use it many times. You keep that in mind. Think about it. We will use them in more problems. You can copy it down, and then I will come up with one more idea, one more plan of doing the same thing, but in a different fashion. But you first copy this down. Alright, so I have this diagram again. Now I wish to do an alternate of constraint relationship which is called the virtual work method. What is it called? Virtual work method. What happens here? Let's look at it very quickly. We assume that this is rising with A and this is falling with A dash, right? This was the thing. This is rising with A and this is falling with A dash. What are we trying to do now? What are we trying to do? Relate A and A dash. So the tension here is T, while the tension here is T dash. The tension here is T dash. Okay. So virtual work method says that net work done by tension is always 0. The net work done by tension is always 0. Why? Because if both are taken into account, tension becomes an internal force, and whatever is the positive work on one part of the system is balanced by the negative work by the other part of the system. So can we say that, let's say this displaces by x upwards and this is displaced by x dash downwards, then if you know the definition of work done, that is force into displacement into cos theta, and it is positive if force and displacement are in same direction, and it is negative if force and displacement are in opposite direction. So very quickly, for 2 kilogram, can we write force is T? Of course we can. Displacement is x, and then we would write cos 0. Why? Because force and displacement both are in the same direction. While for 3 kilogram, we will write the tension is 2T, because T dash is 2T, it's acting upwards, but the displacement is downwards, so we will write cos 180 and then equate it to 0. What does this give us? T is equals to, or let's say T into x is equals to 2T into x dash, or x is equals to 2x dash. Is it giving us the same relationship between the displacements? And again, if you differentiate it twice with respect to time, what you are going to get is A is equals to twice of A dash. So this is another way. You can follow any of the ways. What is more logical is obviously constraint relationship here, where you are just using the fact that overall length of the string can never change. But you can still copy this down, and then we'll take a couple of more examples. All right. Next, so we have a question again, just to get a feel of it. Let's quickly wind this up. So let's say this is T, this is 2G. You can also pause the video and give it a try yourself. What do we have to do? We have to find the acceleration and tension. Okay, what is acting downward is 3G. What is acting upward is 2T. What is acting upward is 2T. But what is acting upward is T. Be very careful. This is 2T, this is 2T, but this is T only, because this is only one string. This whole is a one string. Okay, so the tension in that is T, but the tension in this is going to be 2T. Now would you like to predict who's going to move upward? And of course 2 kilogram is going to move downwards, and 3 kilogram is definitely moving upward this time. So let's start with the correct assumption. So what are we going to write for 2 kilogram? You can pause the video and try it yourself first. So this is 2G minus T equals to 2A. 2G minus T equals to 2A. While for 3 kilogram, what are we going to write? So 3 kilogram is going upwards. So what is the net upward tension acting on it? 2T, 2T and T. So that is 5T. So I'm going to write 5T minus 3G equals to 3A dash. Okay, and now we want a relation between A and A dash. Again, two ways of doing it. First is constraint and second is virtual work method. Let's quickly do that. So let's assume that this moves upwards by x dash. Okay, at the same time this moves downward by x. So when it moves upwards by x dash, length reduces by x dash, x dash, x dash, x dash and x dash. So 5 times x dash. This reduction in length has to be compensated by an increase in length. So you might sometimes be wondering that it feels as if energy is being created. This is the catch. Energy is not being created. Let's understand how. So very quickly, first write this x dash is equals to, or let's say 5x dash is equals to x, and if we differentiate it twice, then we get 5a dash is equals to a. 5a dash is equals to a. So if this is ascending upward with some acceleration, then this will descend downward with 5 times the acceleration. So do you understand? If this moves x, this does not descend by x. If this moves x, this will descend down by 5 times of that. Keep that in mind. Okay, keep that in mind. That is why we can say that energy is not being created, because if it feels that, you know, heavier block is rising, lighter block is falling, but lighter block is falling by what? By more distance, by more distance to compensate for the energy. This is something you will only understand when you know the work, energy, power chapter. So for now, let's not focus on that part, and let's rather focus on how are we relating the acceleration. Okay, so what can be the alternate way of doing it? So it's the virtual work method. What is it? Virtual work method. So again, it's the same thing. The tension acting on it is 5t. We are writing for 3 kilogram first. And what is the displacement? X dash into cos 0. Into cos 0, because tension is also acting upwards and displacement is also upwards. While for 2 kilogram, it is t into x into cos 180, into cos 180, and that should be equal to 0. Ultimately, it's giving you the same relation, that 5x dash is equals to x, or a is equals to 5a dash. So I leave it on to you, but I in fact think that you should know both the methods, so that you can also verify your answer sometimes. And you know, one method can prove to be easier in some situation, and the other can prove to be easier in the other situation. So there's no harm in knowing both of them. Okay, so multiple pulley, I don't know why sometimes students do feel that it's a very difficult thing, but it is very easy. Today we are only doing the basic questions of that, and in the coming classes we can also do a little more complex questions of this, but we'll go there step by step. So we'll wait here. You can copy this down. We'll take another question. Now, if you must have seen that I am stopping myself from solving the equations because it's unnecessary labor, and you can expect such questions only when there is a comprehension where there are multiple situations or multiple things that are asked. But what if we just have to use the constraint relationship in a situation like this? So where A is a block, B is a block, and C is a block, you can clearly see they are interconnected and their motion is constrained with respect to each other. And they have shown us the velocity of A and B, and they want us obviously to predict the velocity of B. So they've given us the velocity of A and C, and they are asking the velocity of B. So very quickly, what method would you go for? So you can go again for both the methods, virtual work method and string constraint. Both the methods can work here. Okay, so let's assume that this is displaced by XA, this is displaced by XC, and therefore this is displaced by XB downward. So we would like to assume that it will descend. These two will ascend and this will descend. Even if we predict something incorrectly, don't worry, the answer is going to be correct, just the sign is going to be negative, which will clearly indicate that you have to assume that the direction is opposite. All right, very quickly then. So first we are doing it by constraint. Imagine this is going up. How much length is lost here? XA. How much length is lost here? XA. So can we write the loss of length is XA plus XA? If this rises, again XC. So how much is the loss again? XC. So this is the total loss. Who is going to compensate this? The gain here. So let's say it falls by XB. So if this falls by XB, how much is the length increasing here? XB, 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 4 times XB. So this is compensated by 4 times XB. So can we say 2XA plus XB is equals to 4 times of XB, or we can write, if we differentiate it once, 2VA plus VC is equals to 4 times of VB. Is this the relation we were looking for? Of course, yes. Now, if we have to predict the velocity of B, can we give the answer? Of course, we can. We put the value of VA as 4. We put the value of VC as 2. So this becomes 10 over 4. So VB turns out to be 2.5. So it's turning out to be a positive value. That means the direction is correct, what you have assumed. Okay. The other way of doing it, of course, it's the virtual work method. So there you will write the work done by tension overall is 0. The work done by tension overall is 0. So what can we write here? We can clearly write T, or is it 2T? Of course it is 2T. Okay, so T is the tension in the main string. Okay, so the tension in these strings is going to be 2T and 2T. All right then. So what can we write? We can write 2T into XA. Since force and displacement are in the same direction, it is going to be cos 0 and the value is going to be plus 1. Now plus T into XC, because T is the tension and displacement is again positive, like in the same direction. But for B, it is going to be how much? 2T and 2T. So 4T into XB, but it's going to be cos 180. So cos 180 is minus 1. So what does this give us? This again gives us 2XA plus XC is equals to 4XB. So is it giving us the same equation? Of course, yes. So I have given you both the options. You can try any of them and I think you should be getting to the answer. All right. If you wish to copy this down, you can do that. And we wish to take one question of wedge constraint today. Not very much, but just a very basic question to understand how wedge constraint works. All right. But I'll give you time. You can copy this down. All right. So we don't want the video to get too lengthy or too long, because then it becomes a little exhausting. So we are taking only one question of wedge constraint today. I'll give you time. You think about all these things, you apply these things, and then we'll come up with further problems. So what is this wedge constraint thing? So you understand string constraint means the total length cannot change. Now what is wedge constraint? Wedge constraint is basically a situation which uses the fact of rigid body dynamics. So if something is rigid, that means it cannot compress or expand. That is what we are assuming here. So you see a 5M block and an M block, and this is some kind of guide, okay, which does not allow this long block to fall or topple, stuff like that. Now, can you imagine if this, since everything is smooth, every surface is smooth, this will start descending, and because of the push, this will start moving forward. So first, are you understanding the wedge constraint here? That because this is falling, it will push 5M, and since it cannot penetrate into 5M, the 5M will have to respond and move in the forward direction. So this A and this A dash is what we wish to relate or interlink. All right. So for that, we need to understand how do we draw the free body diagram. So I will draw them separately now. So you would say mg is going to act in the downward direction. Okay. Let me make it like this. Okay. So let's say mg is acting in the downward direction. All right. Now n is acting perpendicular to the surface. That is the normal reaction. Hence it is called normal. So it is acting normal to the surface. If I can just imagine that this angle is theta, which is by the way 37 degree, then this angle is also theta, then this angle is going to be 90 minus theta, and again this angle is going to be theta. So very quickly I have done the angle part, and now I wish to resolve it. It is moving in the downward direction, so I will resolve the components of n. So obviously along theta it is going to be n cos theta, and perpendicular to theta it is going to be n sin theta. So which direction is this block moving? Downward with acceleration a. So I'm first writing the equation in the y direction. Why not in the x direction? Because x direction, if it is feeling a normal reaction because of the 5M, then that means this block will be pushed towards the right guide, and this right guide will provide a further normal reaction to balance this off. So can you imagine that effectively this block, this long block, is going to be pushed towards the right guide, and that will give it a reaction. But right now we are not interested in finding this normal reaction. So we are just writing the equation in the y direction. So what do we write? mg minus n cos theta equals to ma. mg minus n cos theta equals to ma. That's only the equation in the y direction. Now let's talk about 5m. So let's draw the free body diagram of 5m here very quickly. Okay, so what are the forces acting now? So can I just rewrite the forces? So if it is pushing this block by n sin theta, it will get a reaction in the opposite direction. If it is pushing the block n cos theta upwards, then it will get the same n cos theta downward. What is the other force? Of course, there is gravity, 5 mg. And what is the other force? This is the normal contact due to the ground. Let's call it N2. Let's call it N2. All right. So I've shown the forces. I've shown the components opposite. So if n cos theta on this is upward, so on this is downward. If on this is rightward, on this will be leftward. Where is it accelerating? So it is accelerating towards the left. I've already shown that. It's accelerating towards the left. So I am now only writing the equation in the x direction. Okay. So what is it? N sin theta is equals to 5m into a dash. So I have written the equation in x direction for this and y direction for this for obvious reasons. Okay, but how many equations do I have? I have two equations. I have two equations. But how many variables do I have? I have three variables, I believe. A dash and n. So we need another equation. That is where wedge constraint will come into play. Now, listen to me carefully. What is wedge constraint? Okay, what is wedge constraint? Okay, let me do one thing. Let me take it in another diagram. All right, so let's say this is the common interface. What is it? Common interface. And let's draw the accelerations. So this is accelerating to the right with a dash, while this is accelerating downwards with a, right? So the block cannot penetrate into the other block. It can slide over it, but it cannot penetrate in it. So what I am going to do is I will draw a common normal. What am I going to do? I will draw a common normal. All right. So let's say this is, just give me a minute here. Yeah. So let's say this is A and this is A dash. Okay. So what I am going to do is I'm going to take the components. I'm going to take the components of A and A dash along this common normal. So if you remember very quickly, this angle was theta. This angle was theta. So if this angle is theta, this angle is again theta. All right. So component of A is going to be A dash is going to be A dash cos theta, and this component is going to be A dash sin theta. So I've done the components of A dash cos theta and A dash sin theta. Similarly, this is going to be theta because this is theta, this is 90 minus theta, and this is theta. So the component of A is going to be A cos theta and the other component is going to be A sin theta. Though I'm not very interested in these parallel components, I'm just talking about the perpendicular components. Since it cannot penetrate into this, so however it moves towards this has to respond and move by the same amount. So what I am doing here is I am wanting to equate the acceleration components which are perpendicular of A and A dash along the common normal, So can I write A cos theta is equals to A dash sin theta? Look at it again. A cos theta is equals to A dash sin theta. So A dash turns out to be A cos theta over sin theta, that is cot theta. Now you don't need to memorize it, but still there's no harm that if this moves down with A, then this moves forward with a dash, which is equal to a cot theta. So if we go back to the previous page, then if we use the wedge constraint equation, that is a dash is equals to a cot theta, and since theta is 37, you can assume, you can put the value of theta 37 and get the value of cot theta, that is obviously going to be 4 by 3, because tan 37 is 3 by 4, so cot 37 is going to be 4 by 3, and easily solve these equations. So this is where you are using the wedge constraint in a very simple situation, but we will come up with complex problems also. But again, you have to understand how this wedge constraint is working, that the acceleration component along the common normal has to be equated because they are rigid blocks. This is how wedge constraint is working, and ultimately it's looking like a dash is equals to a cot theta. So if this is a, this is a cot theta. If this is a, then this is a tan theta, obviously, but I'm not wanting to confuse you here. Again, if this is a, this is a cot theta. So that's about the constraint relationship related with strings and related with wedge. I hope you were able to understand most of it. If not, then you can obviously re-watch the video. You can slow down and think again, and then watch the video, try some question, then watch the video again. But ultimately, I think I've accommodated the major information in this video that would help you a lot, and this was my best effort, and I hope that you will also put your best effort now, and we'll come up with more such videos. Thank you very much for your time, and I will see you again. Bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.